Okay, sorry for the delay due to technical problem of our classroom system. So this is the lecture 14 and this is the last lecture before our midterm examination. So once again, please come to our classroom on next Tuesday, so 9 o'clock. So please bring your calculator because you have to use them. Okay, then others is that everything is just normal as other usual paper examination. So now let's review our previous lecture 13. One of the questions from our students was the analytic solution of homework number 4. So there are two problems, but they are quite similar. So I will just consider the case for up node V2. So we are now considering the case of, yes, the first one and the second one, and we apply input voltage as a function of time, and we wanted to measure the output V2. This is the case. So if you wanted to take the Laplace transformation of this one, then it becomes just R, and this transformed space, it becomes 1 over SC. So this is quite well known, so you can do it quite easily. And from this one, then you can, so let's say that this is now transformed into the S domain input voltage and S domain output voltage. Then this transfer function can be written as this form. Of course, in order to get this one, we have to do some manipulation, but anyway, you can do it. So this is voltage transfer. After that, we have to calculate the step response when we so please wait, because once again cancel this stuff. Okay, so in this case we have to calculate the step response, and in this case our input voltage can be regarded as 1 minus u over t. So here u is unit step function. So we are now considering the case where our input voltage suddenly become 0 from 1. So however, this one, it is not considered in our Laplace transformation, so we just calculate the step response of our system. So first we consider the u over t as an input signal. After that, we will introduce a minus sign, and we'll consider steady state response of our DC input 1. Then we can recover the final solution of our output voltage V over 2, V sub 2 to t. So this is the step response function. So step response function is simply given by this adding 1 over s, because b1 as this unit function, unit step function can be written as or transformed into 1 over s. After that, you can find that this output voltage have the sum of something. There is one pole and another pole, and 0 is another pole. So they can be decomposed into this form. So yes, they are expanded. And how can you calculate this coefficient? So I just use introduced certain unknown variables and try to match it. So simply speaking, I assume that this V2 can be written as S plus 1 over tau 1 and alpha, and say beta x plus tau 2 and gamma. Then let's say that these should be identical with our correct expression for v sub 2. Then we can say that here we have only one leading coefficient 1, so second order term should be 0, its coefficient, and first order term should be also 0, and finally we must have only zeroth order term equal to 1. So from that calculation you can easily calculate these numbers, although the calculation will be lengthy, but anyway you can easily do that. So after that, since they are all written in the basic function, so we can take the inverse Laplace transformation quite easily. So we just keep the coefficient, and this one is transformed into this exponentially decaying function. Also we have exponential decaying function, and this 1 over s is transformed into unit step function. However, as I told you before, uh, this response is only for when we have input signal of u of t. However, we must consider 1 minus u of t. So first of all, we have to introduce negative sign and negative sign and negative sign here. This takes into account this minus u. And finally, we have to consider 1. What is this response of our system when our input voltage is constantly 1? Then you will find that this is just gives you 1 every loop. So this minus u, which is always 1 at positive t values, and this one is cancelled out, so you have only decaying function as expected. So now you have these two time constancies, tau 1 and tau 2, and that they were defined in this way. Okay, this is only for problem 1. However, if you start from the transfer function v sub 1, you can find also similar value. So please calculate your analytic result, analytic solution with this one. That was my quick answer to your question about the analytic solution. So there is no like a explosive solution in this one. So this is just decay in this case. And another question from our student was parasitic delay of 2-input NAND gate. So please have a look at the table we have already seen in our previous lecture. So here you can see that 2-input NAND has the normalized delay of 2. So one question was why we have a normalized delay, parasitic delay of 2. So in this case, please let me just come back to my previous explanation. So first of all, we consider size of 2 for our P MOSFET. After that, we introduce also N MOSFETs. 2 is this is the given sizing of our standard 2-input NAND gate, and we found that this is given as 6C. So it is now assumed that they do not share this drain, and each of them contribute to 2C, and this one also contribute to 2C, and finally this N MOSFET contribute to also another 2C. So we have 6C, and now we have R and 6C. So that's the reason why we simply estimate 6 times RC, which can be given as, for example, parasitic delay equal to 2. That was my previous answer to this question. And after the session was over, I got a question from our students. If we really calculate this delay with this system, then maybe we can find a little bit different conditions. For example, even though we have 6C, if we consider certain thing like another 2C in between this drain and source of our two transistors, then we can draw something like this. Half R due to our first transistor and another half R for our second transistor, and here we have 2C and now 6C. So previously in my calculation I just consider this one, so 6C times 2C. However, as you know, if this is really the calculation of Elmore delay, then if we consider this another leaf capacitance here, whose capacitance is 2 times C, then we must consider this shared part once again, because this is the this is the output node and this is the leaf node. Then this half R is shared by these two roots, so we must consider half R times 2C to calculate this one. So we have additional RC. So simply speaking, in even this sorry about that, so falling edge, so we must have this RC additionally, so that will be not exactly number 2 but 7/3 will be the parasitic delay. So question was, then why we have this number 2, and why number 3 and number 4? So the answer is quite simple. The answer is these values shown in here are not as accurate as calculating all kinds of detailed analysis on this RC network. So simply this is obtained from quite a simple argument just I did in our previous lecture. So please consider this one. For example, let's consider a general case of n input NAND gates. So here we have n copies of P MOSFET, and let's say also n copies of n MOSFET. Please try to size them. Then how can we make their sizes? So in the case of our P MOSFET, still we will have number 2, and still we will have number 2. Why? Then each of our transistor can provide the unit effective resistance R. So now everyone, this one, another one, and anyone can provide effective resistance of R. However, in the case of our pull-down network, we must a little bit careful, because each of them should be actually R over N. Only when we have R over N for each transistor, then when sum them all, then we will have the resistance corresponding to the effective resistance R. So simply speaking, in this N input NAND gate, so the recommended size of our N MOSFET is given by this one. Then let's try to find out the capacitance seen from this output node. Then each P MOSFET will contribute to 2C, 2C, and 2C. So since there are n copies of P MOSFETs, so we can expect that from P MOSFET we will have 2n times C. And also here we have quite wide n MOSFET, and it will contribute also NC. So simply speaking, this calculation gives us 3C times N as an output capacitance of our our no our N input NAND gate, and its effective resistance is also considered as just R because we have already done it here. So that's the reason why the tau or P or tau due to the parasitic delay will be simply given by 3RC times N. When normalized by this 3RC, then we have just number N. So as you can see, this is nothing but just a generalization of my previous explanation for number 2 case, 2 input case. So in this discussion, there is no consideration for this leaf node. So here, in worst cases or worst cases, we can have many other leaf cases which can additionally contribute to tau. So I mean that if we just do the calculation for pull down network, then things becomes a little bit more complicated. So let me just simply sketch the situation. For example, let's say we have case like this. Now we have so 3C times N, and here we have R over N, and here we have additionally something like this. Here we have C times N. Also here we have R over N and C times N. There will be the list of chains of these kind of calculation. We have already done only terms related with this one. So if we have to consider this one, another one, another one, we must be careful about that. Okay, so please try to formulate this overall Elmore delay, so you can do it quite easily, and the answer will be the Elmore delay calculated from this way does not necessarily follow this linear dependence. So you can find also second order quadratic dependence term to your delay component. So it means that if we increase this n values too rapidly, or if n is too high, then when we compare this linear dependence and second order dependence, eventually this second order dependence will be a dominant term. So it is not desirable to have too large n values. If you set n value too large, then your parasitic delay will increase too rapidly. So this is not a desirable condition. So let me just conclude my answer. Simply speaking, the question by our student was really correct. It is because this table itself is a rough estimation on parasitic delay. If we are just we really wanted to calculate the exact value of propagation delay in terms of parasitic delay, then we should be more careful. So please have a look at this table as a just rough estimation of about our parasitic delay. Finally, I wanted to raise this my final comment on this number 2. Up to now, we have assumed that even in the case of our our two input NAND gate, so we have assumed that yes, it has number 2 both sides and number 2, and I have assumed that each of them contribute to C and additional 2C. That's the reason why we have 4C out of our 2 transistors. However, you know that there is a trick to reduce our diffusion capacitance. For example, in this case, if we have, and if we draw in this way, and if we use this one, this shared diffusion area as a common drain of our 2P MOSFETs, then we can actually reduce the value of our diffusion capacitances. So simply speaking, this is not quite much strict value, but even for depending on the layout style. If you have a different layout, then you can change it additionally. So simply my answer is this table is not that accurate, so please treat it as a rough estimation. So that was my answer. But anyway, that was a really good question. And the last slide I have prepared for my previous lecture 13 is effective effort delay explained once again. So of course we have already covered the effort delay, but I wanted to repeat my explanation once again. Yes. So please consider a logic gate whose width is k times wider than the unit 1. Here unit 1 means that unit 2 input NAND gate or unit 2 input NOR gate or any kind of n input certain logic gate. Yes, think about that. However, we just scale its width uniformly to have a more powerful driver. So now let's think about this one. Then, since this unit logic gate has the effective resistance of R, so if we have k times wider logic gate, then what will happen to its effective resistance? So of course, instead of this R for our unit gate, then we will have R over K. We can have this reduced value. So we have this reduced effective resistance, and since we are now talking about effort delay, so its own parasitic capacitance doesn't matter, and we are only interested with the C out of our system. Okay, are you with me in this case? So of course we have to, in general, propagation delay is determined by its own parasitic delay and output capacitance. However, this part was already considered in our parasitic delay part. So when we consider effort delay only, then this does not contribute. So the only thing we have to consider is like this. So simply speaking, the tau due to the effort can be simply written by these two products. the effective resistance of this wide logic gate and output capacitance attached to its output. And now you understand we have already introduced the fan out or electrical effort F. This F, oh sorry F, not F, this is H. This electrical effort or fan out simply states the ratio between our input and output capacitances. So now this C out can be represented as H times C in. Yes, that is shown here. Then now finally, how can we evaluate this C in input capacitance? Input capacitance is given by, if we have unit gate, then it will have this capacitance as its input capacitance. You know, nothing but this logical effort means that how large is the input capacitance of our logic gate compared with 3 times C, which is the reference value of the unit inverter. So smallest inverter. So now everybody can understand this is the one for our unit logic gate. However, we have assumed that already we have made K times Y the driver. So instead of this mere 3C times G, but we have to also consider K because we have a wider driver, so it has a wider area, so capacitance is scaled exactly with this factor. So if we just introduce this one, then tau can be obtained by R over K times 3C GK finally times electric effort, as you can see here. So they are cancelled out. Then we have 3RC times G logical effort times electrical effort or fan out G. So you know this 3 times RC is regarded as a reference value for our propagation delay. So if we divide the left hand side and right side with 3 times RC, then we can have clearly the effort delay is given by logical effort multiplied by electrical effort or fan out. That is my simple restatement of the textbook explanation. So I think that to somebody, maybe it is more intuitive or more easy to understand. So if you have any question, then please let me know and please interrupt me.
그래서 K가 그러니까 인풋 쪽을 K를 내리는 건가요? 아니면은 그러니까 로드 쪽을 K를 내리는 건가요? 아니면은 그 드라이버 쪽을 K를 내리는 건가요?
Okay, his question is, what is the exact meaning of this K in this case? Yes, thank you for your question. And now my answer is quite simple. Now think about this one. Here we have C out, and this is driver or logic gate we are considering, and this is output, that is load. And now I'm saying that we have scaled our driver with 2 times, 3 times, or 4 times. This will be the K will be the size for our driver. So this is not related with our C out. So if we have a higher K, then we have stronger driver. So we can expect that the driver becomes more hot.
그 유닛 인버터, 그러니까 유닛 인버터의 그 캐패시턴스를 3C로 봤는데 그 K 타입이 되면 3KC가 되는 걸까요? 그러니까 원래는 이게 3C가 유닛 그
3C, that this 3C is the capacitance, input capacitance, capacitance of the unit inverter. So logical effort of a certain logic gate is normalized with the input capacitance of a unit inverter. So for example, let's say for example C equal to 4 over 3 for a 2 input NAND gate. Why we have 3 over 4 over 3 for 2 input NAND gate? It was because we have number 2 and number 2 for their sizes. So we can see that 2C from our P MOSFET and 2C from our N MOSFET. They are all matched or all connected to one input of our 2 input NAND gate. So we have 4C of input capacitance, and that was normalized with the 3C, which is the reference value. That was the logical approach of our logic gate. So simply speaking, if we just multiply 3 times C to our logical approach, then we can recover the input capacitance of this unit 2 input gate, 2 input NAND gate. However, this is all related with under assumption of 2, 2. How about this one? If we increase instead of 2, if we have a size of 2K and 2K, then what will happen? Everything will be just scaled by this way. So we will have 4C times K. But still, we have to have the, okay, so therefore, this 4C times K can be, the C in can be written as this one, the relation between unit size ones multiplied by our size factor. So however, point is here we have sizing factor related with this input capacitance, and that is compensated by the one for our effective resistances, so they are cancelled out, and the final representation is simply this one is the property of type of logic gate. So even though you have a wider logic gate, or if you have a narrower logic gate, that does not change this G logical approach. The only change occurs here, H value. For example, think about this one. Think about the case of K equal to 1 and K equal to, for example, 10. What happens? In this case, you will find that G, the logical effort of these two cases will be the same. Then, what is the difference between these two cases? So H is given as just a ratio between our input gate, input capacitance and output capacitance. So if we have 10 times wider driver, then we can expect that our C in can be increased by factor of 10. So compared with this unit sized one, this 10 times wider one has 10 times smaller electrical effort or fan out. So therefore we can expect that it can have 10 times shorter effort delay. So that is quite much reasonable in terms of our calculation or our intuition. So if we have a powerful driver, and if it has the same load, then powerful driver will take much shorter time to drive that same amount of load capacitance. That is reflected here. So that is quite easy thing. However, that is formulated in this way explicitly to divide the type and size. Then where do we have size effect? Size, all kind of drivers size effect is consumed in this H factor, so electrical effort, and G, the logical effort, does not have any dependencies on its size. So we can concentrate on only H to calculate this effort delay. Okay, but maybe you may have additional questions, so it is always welcome to have any question once again. So please interrupt me if you cannot understand this concept, then please let me know. So up to now we have considered a single stage, but we have to consider also multiple stages. So I think that we will have quite a short discussion about this logical effort of classes, and we'll wrap up today's lecture. So the midterm examination will cover up to the end of our today's lecture content. So please prepare your midterm examination. So now think about a seemingly complicated multi-stage logic networks. So now we want to calculate the total propagation delay from this input node to the output node. Then how can we calculate this overall propagation delay? That is quite simple. You have to consider the propagation for this first stage, second stage, third stage, and fourth stage. So each stage will contribute its own propagation delay, and by sum them all, we can find the overall propagation delay. That is quite simple, and you know each of them has two terms. What was it? One was the parasitic delay and one was effort delay. Also, this second stage can have its own propagation delay, effort delay, propagation effort. So now we can understand they will contribute. So as you can see here, the total propagation delay D can be obtained by the contribution from first stage, second stage, third stage, and the last stage. And what is the value shown here? The one for inverter, number 2 for our NOR gate, number 2 for our NAND gate, and number 1 for our inverter. So simply speaking, these numbers are all related with individual parasitic delay contributions. Okay, and also we have effort delays. So effort delays are written as this form. For each one, we have to consider this kind of thing. It has the inverter has a logical effort of 1, and let's just say that its electrical effort is given by these numbers. Please note that here we have 10 x, y, and z, and please note that these numbers just represent the output input capacitance of our each logic gate. So for example, when we calculate H1, what should we do? So we must consider C in of the first stage, and we have to calculate C out of the first stage. Then as you can see that here that is given as x over 10. Why it is x over 10? Because we have assumed that this C in of our inverter is given by 10, and C in of our second stage, which is corresponding to the output capacitance of the first stage, is given by x. So this is x. Same can happen to the second stage. Its input capacitance is x and its output capacitance is y. So we have x and y over x. Same happens for this one, and finally have this one. So please regard these numbers not just the size but for their capacitances, input capacitances. So anyway, now we must have this kind of value. Then, so as a designer, we wanted to change this x value and y value and z value to minimize this d value. So if you say, maybe it seems to be quite easy at the first glance. By changing x, y, z, minimize this d value. Then, since we have linearly dependent term, it is easy to say that, okay, if we have very small x value, maybe we can achieve the small d value. But unfortunately, please have a look at it. Although we have a linear term in x, however, here we have additional x. If we have x, quite a small x, to reduce or minimize the contribution from this first stage, then there will be the increase of this second stage. So let me just explain in another way. Okay, so simply speaking, this one x is corresponding to the input capacitance of our second stage. I wanted to reduce it because if we have small two input NOR gate, then from the viewpoint of our first inverter, load becomes quite small, easy to handle. So that is shown here. However, unfortunately, if we have a very small NOR gate, then it cannot drive our third stage, the NAND gate. That is shown here. So simply speaking, we have to have some optimal point to minimize the overall propagation delay. It is not just one directional monotonic problem. So we must find out what is the best value or optimal value for x and y and z. That will be the case. Okay, so are you ready? So problem is quite much appealing. So because somebody can say that, okay, if we have this one, then we can run the computer simulation. Then by changing x and y, z all over design space, then eventually we get the best value. But you know that this problem is just having the small number of variables. However, in reality, we will have much large number of design parameters. So this kind of near brute force calculation will not be quite much effective to our calculation. So we wanted to find out a good way to minimize this propagation delay. Okay, are you all with me? Then we wanted to minimize the propagation delay. How can we do that? So simply speaking, from this calculation, it is quite obvious that parasitic delay does not play much role in realize the minimum propagation delay because they are just given numbers. By changing our sizes, but not any effect actually occurs in their propagation delay. So therefore propagation delay can be regarded as just a given number. So as a designer, we must find out the XYZ to minimize this number. How can we minimize this number? So that's the reason why effort delay is important in this calculation. So if we consider just one single stage, yes, sometimes they can be quite much comparable, but you know that in this case, if we consider certain path, then we must design something. And in the case of designing, the sizing is not affecting this propagation delay. Then how can we minimize this effort delay? So now we have to understand this inequality between arithmetic and geometric means. Okay, we have, for example, a sum of 4 different numbers, 1, 2, 3, 4, and from this inequality, then you can see that the arithmetic average is always larger or equal to this geometric means. Simply speaking, if we wanted to minimize this sum, simple sum, then we have to find out this equality condition. And when we get the equality condition between arithmetic means and geometric means, then when each of them are equal to the others, then we can have this minimum values. So simply speaking, if all of these 4 terms are the same, yx, the third term, when they are all the same, then we can say that this one will become just 4 times. So product of x over 10, 5 over 3, yx. So sorry about my ugly writing, but anyway, you can easily understand this will be the situation for our effort delay. Finally, very important observation is it is cancelled out. It is also cancelled out. Also, these are cancelled out. So, do you remember what is the meaning of x, y, and z? They are all input capacitors of our intermediate stages. Please come back to here. The x is the input capacitance of our second stage, third stage, and first stages. And only remaining term is, please have a look at this one. We have the remaining term like 10 and 20. What is 10 and what is 20? That is the input capacitance of the very first stage, and 20 is given by the output capacitance, the load capacitance of our entire path. So intermediate terms like x, y, z are gone, only because they are cancelled out. If you increase x, then your first stage will be suffered with increased load. However, your second stage will be good, will have some additional effect, advantageous effect to drive this third stage. So they are cancelled out in terms of propagation delay. So the remaining term is just like this: 12 or 20 over 10. This is C overall C out over overall C in times. Here you have 5 over 3 and 4 over 3. What are they? They are actually logical efforts of test logic gate. Okay, so here we have logical effort of 1, 5 over 3, 4 over 3, and 1. So we just have product between them. Please note that previously we had here logical effort, and logical effort given in summation form. However, using the inequality between these two averages, we just convert it to what? Into a product term. Then product term allows us cancelling out these sizing effect, and also just convert our previous summation form into product term, and now we have product of logical approach. So that is quite simple. So if we apply this kind of thing to our example, then now we can see that this is parasitic and this is effort, and you can see that there is a minimum value corresponding to this number. Okay, then if we really, please have a look at this one. What is it? It is just a constant. Why we have a constant although we have x, y, z? It is because we have already applied the minimum condition for our d value. In that case, they are all cancelled out, and this number only depends on finally C out over C in and your G1, G2, G3, and G4. So a product of your logical effort. So that is quite easy and elegant way to minimize the effort delay. So simply speaking, let me summarize today's talk. So then if we have a certain n-stage path, then minimum possible delay of an n-state, sorry about that, n-stage path, then n-stage path can be given by the path effort that is just given. So once you have a logic gate and effort delay, and this effort delay simply given by this form. Yes. And what was the path effort? Path effort is nothing but the multiplication of all of your logical effort G1, G2, G3, and G4, and finally consider C out over C in. That will give you this number F corresponding to, in our case, 40 over 9, and you have this number. Then maybe it is too complicated at a first glance, but if you go to this example, maybe it is not that difficult. So now let's say that we have load which is given as 64. This is not set by your design, because this will be used some a part of a certain system. The spec for your data pass load 64 is just given, and you are enforced that your initial driver has the size of 1. The remaining thing is you are free to introduce additional inverter chains to minimize the delay. So now let's do this job. First, think about this simplest case. You have just one inverter, only one inverter, and you have a data pass load of 64. Then what will be the overall delay? In this case, yes, there is only one single stage, so you have to consider the stage's parasitic delay, just one, and its logical effort also 1, and multiplied by what? Multiplied by its fan out. In this case, we have 1 and 64, so it will be just 64. The answer will be 65. It is quite reasonable because we have a very small inverter driver and try to drive 64 times wider load, so it will take quite a long time to drive this one. Then now let's think about this one. Now we have no idea. Let's say that, let's call it as X. Then what will happen? So if we have 1 and X and 64, if we just follow this simple example, then our D will be given by 1 from first stage and X for our first stage. This is the contribution from our first stage. And how about the second stage? In the case of the second stage, also it will contribute to 1 because it has its own parasitic delay, and we have to consider the fan out. From the viewpoint of this X times wider inverter, 64 is no longer seen as 64. This one is seen as 64 over X. Okay, so this is the contribution from our second stage. So we have to minimize this 2 plus X plus 64 over X. Then it can be minimized by saying this one and this one are identical. The identical condition is X equal to 8. Then in this case it is 8, and this is 64 over 8 is also 8. So we will have 18. Okay, this one gives us 16 and plus 2. So now we have 18. Already you can find that compared with this naive one, without any intermediate initial driver, the delay can be reduced quite a lot. So simply speaking, if we introduce intermediate stages, because each of them can drive a slightly larger and larger one, then we can decrease the delay significantly. Of course, please have a look at this one. Of course, although we have reduced this number, so this number is now 16, effort delay becomes 16 compared with this 64. However, we have increase of what? Increase of parasitic delay. Although parasitic delay is increased, but its increment is quite marginal, just number 1, and its reduction is quite huge, so it is justified to introduce this additional stage. But now think about another case. Now, wow, that was good, so I wanted to keep this way. Once again, why don't you just introduce 3 stages, and let's call it as x, and let's call it as y. Then we will have once again 1 plus x, 1 plus y over x. Finally, we will have 1 plus 64 over y. So what is the minimum condition, minimizing condition for this sum? So you can see that that can be minimized as 3 times and 3 times of third of x, y over x, and 64 over y. So since logical effort of this inverter is always 1, so that's the reason why we have no contribution from this logical effort. However, if we consider different logic gates, please note that we have to consider the product of all intermediate logical effort in the past. So that is simply 1 in our inverter case. And now you can see that all intermediate values are gone, and the minimum value is given by 3 plus 3 times, so 64, and it's further. So here this number is given, and when you calculate this number, this number is, this will be just number 4. So 4 times 4 times 4 becomes 64. So we will have 3 plus 3 times 4. So we have 15. Yes, this one becomes 15. Although compared with 18, this is still, or there is still a reduction, but not drastic as the case between n equal to 1 and n equal to 2 case. So now if we keep this way additionally, then we will find that actually there is bounce of this delay. So by using this kind of calculation, then we can conclude that, okay, if this data path load is given by 1, then maybe the third stage implementation will be the most effective way to reduce or minimize the propagation delay. It can be the delay of delay analysis using the logical effort can be used in this way. Of course, we have much more examples in the textbook about logical effort and its application to the path delay, but I just wanted to wrap up today's lecture, and that will be the end of our discussion on delay estimation. So please note that, please remember the first session of our delay discussion. When we start, we already covered that the exact estimation of our propagation delay can be done with spice simulation. If you learn the spice simulation, then you will get accurate estimation or prediction for your timing. However, the reason why we are doing this kind of a crude approximation is not for having the accurate value, but get some hints for designing our system. So please understand the background or motivation to do this kind of approximations. Okay, then I want to wrap up today's lecture and see you next Tuesday in the midterm examination. Thank you.
딜레이를 줄였는데
Okay.
안 좋아지는 건 없나요?
Oh, of course. So, okay, I will thank you for your question. I will quickly answer his question. He asked me, oh, as much as we understood, then by adding these additional stages, we have the reduction, significant reduction of propagation delay. Is there any negative effect in terms of other metric? Yes, of course, we have already spent, you know that, the size of our silicon was unit sizes. And now you have 21 times wide space spanned for this driver. It means that, once again, also we are using large silicon size, and area is one of the most critical factors we have to consider. Although we have implemented fast circuit, however, this one is wide circuit.
파워도 많이 들어가는 거죠?
Yes, sure, because we have to have also not only charging this 64, but we have to also charge and discharge the internal capacitances here. So from the viewpoint of power consumption, so that is not that much beneficial. So it means that in order to get performance, once again, performance can be regarded as a frequency, speed. If in order to get high performance, we have to sacrifice something. That is almost always the power and area in this case. Okay? That's a good question, and thank you.